Welcome everybody in the dynamic section of this year's virtual ICM. Our speaker today is Corinna Ulcigrai from the University of Zurich, and her title is Dynamics and Arithmetics of Higher Genus Surface Flows. In case you have questions, you can post them after the talk on Discord and she will get back to you. Please, Corinna.
Thank you. First of all, let me say that it's of course a great honor and pleasure to be given this talk. And as you saw from my title, Dynamics and Arithmetics of Surface Flows, I want to touch upon these two aspects in the study of surface flows by trying to giving a bit of a survey on some recent developments in this area, and mostly focusing on the ergodic theory, spectral theory, and linearization questions. But the emphasis will be on what I call arithmetics, so on Diophantine-like conditions for higher genus flows. So I'll try to explain what this means and what they are and why are they crucial in the recent developments. But let's start slowly. So let me start with a bit of notation introduction. So S will be a surface throughout the talk, always orientable, closed, compact, connected. The genus will be one or more, and we will look at the flow on the surface. So I take a point, and as I flow, I get a trajectory or orbit. I will use trajectory or orbit. You could imagine that you have differential equations that give you the motion on the flow. And okay, this is an example of your point moving along a trajectory. And not all the talk, but a good part, I will deal with area preserving flows, because this is a natural setting for ergodic theory. So mu will be the measure, a two-dimensional measure, which is fully supported and not atomic. And many times we'll have a smooth manifold, smooth surface, and a smooth area form, which gives us the area. And again, the flow preserves this area, so it's incompressible. And an important remark that when we are in higher genus, so genus at least 2, it's unavoidable to have fixed points of the flow. So I call them singularities. And this can be a center. This is a picture of a center, or it could be a saddle. And the saddle can be simple when there are only 4 incoming prongs, or degenerate when there are more than 4, even number. And again, in this picture of the center, you can also see a saddle loop. So it's like a half figure 8. A saddle loop is a trajectory that goes from a saddle back to the same saddle. Okay, so why shall we study surface flows? Well, the study of surface flows is intertwined with the study of dynamical systems. And it's really one of the fundamental examples, since it goes back to Poincaré, the interest in surface flows. So Poincaré is also the father of dynamical systems in general. And his interest came from celestial mechanics and describing the motion of planets. And he often reduces it to study of flows on tori. But a very nice example of higher genus surfaces arise from solid state physics. So the so-called Novikov model of electrons in a metal. So this is a model which was suggested by Sergei Novikov and much studied in the 1990s. And the idea is that when you have a magnetic field and use semi-classical approximation, the motion of the electron is constrained to the Fermi energy level surface. So this is an infinite periodic surface, but you can quotient it, look at the periodic cell and get a compact surface. And the flow that you get is really a smooth area preserving flow. The setting we want to consider. But I must say that more than physics, my main motivation to like surface flows is that to me, they are really one of the most important examples of slowly chaotic or parabolic dynamical systems. So what do I mean by slowly chaotic? Chaotic systems have the butterfly effect or sensitive dependence on initial conditions. And by slowly chaotic, I generally are systems where the butterfly effect, so divergence of nearby trajectories, happens slowly, and slowly means sub-exponentially. It could be polynomially or subpolynomially. So there are in general rough division into three types of dynamical systems: hyperbolic, where divergence is exponential and entropy is positive; elliptic, and where there's no divergence or very slow; and parabolic is kind of intermediate. And the famous examples are Hollow cycle flow, negatively curved surfaces, or unipotent flows. But contrary to hyperbolic and elliptic dynamical systems, which are much more studied and understood, parabolic dynamical system, there's no general theory. There's such a few examples that we understand well. And I want to tell you that now I understand also flows on surfaces fairly well, but still there are more open questions. Okay, so together with the flows, we will also look at discrete dynamical systems that you get as Poincare maps, so associated to the flows. So the idea of Poincare map is, again, idea of Poincare of considering a section to a flow which is minimal, and looking at the map from the section back to the section that you get by following a trajectory until the first return time. So if I take the Poincare first return of a flow on a torus, let's say smooth and minimal, the Poincare map will be a map of the circle to the circle, and it will be a circle diffeomorphisms. And this is a picture of a circle diffeo as a map, as a graph. This is the graph of on 0, 1. And even though the circle diffeo is continuous, when I represent it on 0, 1, it has two branches, the blue and the green. And it's also important to have linear models. So an example of flow is simply the linear flow, which you obtain by moving on straight lines with a certain slope. And in this case, the Poincare map is a rigid rotation, x plus alpha mod 1. In higher genus, when we look at the Poincare map, because singularities are unavoidable, the Poincare map has discontinuities. So it's really not continuous. It's a one-to-one, almost one-to-one map, but it's piecewise continuous, and it's a piecewise diffeo. And this type of maps are known as generalized interval exchange transformations. So they exchange the continuity intervals, and on each continuity interval, the map is a diffeo which extends to the closure. And a linear model is given by linear flows on translation surfaces. So if the surface has the structure of a translation surface, this is the right structure where you can talk about linear trajectories. So you have a flat metric and the notion of direction, and you can have examples of linear flows in higher genus. In this case, the Poincare map is not only a piecewise diffeo, but it's actually a piecewise isometry. So each interval is translated, and we talk about interval exchange maps or interval exchange transformations. Okay, so which questions are we interested in? So there are many questions you can ask. You can ask topological type of questions. For example, if there are periodic trajectories, dense trajectories, or what can the closure of a trajectory be? For example, this is a picture of a minimal component. So this is a subsurface with boundary on which every infinite trajectory is dense. We'll have minimal components again later. Another type of question is the so-called linearization type of question. So we saw that we have natural linear models. So you may want to know if you can conjugate your nonlinear flow to a linear model. And if you have a topological conjugacy, you want to know what is the regularity. And this is important, for example, if the conjugacy is a list C1, and you have a natural invariant measure for the linear flow, like Lebesgue measure, you can pull it back and get a nice invariant measure for the nonlinear model. And when we have a nice invariant measure, we may want to study ergodic and spectral properties. So ergodicity, mixing in various formulation of mixing, weak mixing, strong mixing, mixing of all orders, or also have finer notions like spectral properties, the nature of the spectrum, joinings, and so on. So the next two slides, I want to give a very brief, big picture of what do we know of these three aspects in the case of genus 1 versus higher genus. So for genus I, essentially, it's the classical theory of circle diffeos, which gives us many answers. In particular, the topological type of questions were essentially go back to the work of Poincaré, maybe Denjoy. And it's Poincaré introduced the rotation number of a circle diffeo, which is a key invariant. And you can understand if you have enough regularity in this C2, then rational rotation numbers correspond to the presence of periodic orbits, and irrational rotation numbers plus regularity give minimality. So this is okay. And linearization, it's also classical. You have a local version of the linearization question when you start from a diffeo, which is a small perturbation of a rotation. And then this is essentially the realm of KAM theory, Kolmogorov, Arnold, and Moser. And of course, a huge area of research. And among global results, when you don't assume that your diffeo is close to a rotation, then a celebrated result is Hermann Yoko's theorem in the C-infinity category. And when you want to do linearization, for example, in C-infinity, you really need not only to assume that the rotation number is irrational, but you need Diophantine conditions or arithmetic conditions. So you need to know how well or how badly approximated by rationals your irrational rotation number is, and put assumptions on this. And then you can do ergodic theory. In this case, for Diophantine, almost every rotation number, it's quite clear what the properties are. You have unique ergodicity, you don't have mixing. But you can create still unusual or exceptional dynamical ergodic behavior when you look at measure zero set of rotation numbers, the so-called Liouville numbers. And then there are many people, so I just put some names, Katok and Fayad in particular have worked on producing Liouville exotic examples. Or you can add singularities. In genus I, you can add singularities, and then you also can get interesting ergodic spectral properties. How about a higher genus? Well, in higher genus, topological questions are again very classical, and it's really, this goes back to Poincaré and Bendixson, and then I put a number of names here, but by no means complete. And there is a nice book by Nicolai and Tsutsoma, which surveys mostly topological questions. And I would say in the 30s and 40s, there was a lot of activity, 1930s, 1940s, and also again, a bit of revival in the 70s. And for example, the work of Leavitt. And so topological questions are very classical. And another classical, by now, classical aspect is the ergodic theory of linear flows. So again, this is somehow connected to Teichmuller dynamics, which started in the 80s with seminal work by Howie Mazur and William Veitch. So ergodicity of almost every linear flow, and then also Herkomezou-Smiley work about ergodicity, and was proven in the 80s. And then also Katok proved the absence of mixing. And weak mixing took a bit longer, so it was an open question until Avila and Forney settled it a bit later. But somehow, ergodic theory of linear flows is relatively well understood, and there are still spectral questions open, but it's, I would say by now, still classical, this part. On the other hand, if we want to study smooth area preserving flows, preserving a smooth area form, so-called also locally Hamiltonian flows. So these are the flows that come from Novikov model, which I mentioned at the beginning. Then the history is much more recent. Actually, this was what I started working originally already in my PhD thesis. So about 10 years ago, first Sheklov had the result in genus II, then I worked on it. Then Ravoti is a PhD student of mine who worked a bit later, actually. But mixing is essentially, I will tell you in a second, what we know about mixing. And after this about 10 years ago activity, just a few years ago, myself and other people went back, the co-authors also mine, we went back to study finer properties like Rattler property, disjointness, and I will mention some of these results later in the talk. But somehow I want to stress ergodic and spectral theory of smooth flows is much more recent, essentially 10 years ago and recent ongoing work. And linearization, what about linearization? So the question is very natural. So you would like to have a KAM theory in higher genus. And very seminal work by Giovanni Forni showed that actually there are difficulties, there are obstructions, they come from cohomological equation. I will mention some result later. And Marvi Musayi revisited Forni's work and could prove a result in this direction, the best you can do in, I will go back to this again. And recently also Selim Ghazouani and Elon and some joint work, we also had some recent advances they want to mention. So what is the outcome of this overview? Topological questions, very classical. Teichmuller dynamics, ergodic theory of linear flows, 1980s, quite well established. But the other two aspects, linearization and spectral ergodic and spectral theory of smooth flows, are much more recent. Why? To me, because these results require the use and the introduction of some version of Diophantine type conditions on for a higher genus setting. So I want to now stress what do I mean by this? So let's go back to genus I and to Diophantine or arithmetic conditions for the torus. Arithmetic conditions means conditions that tell you how well alpha, which will be our rotation number, is approximated by rationals. And the prime example is the Diophantine condition. I wrote it down here. It's a condition that tells you that alpha is quite far from PQ in a quantitative way. And I like to think of these conditions can be also expressed by continued fraction entries growth. So you can write your alpha into a continued fraction expansion with entries AI. And equivalently, for example, the Diophantine condition, you can write it as a cross condition on AN growing like Qn to the tau or some tau. And Qn is the denominator of the partial convergence. Other conditions like rod type, AN is of Qn to the epsilon for every epsilon, or bounded type, the entries are bounded, can be expressed through continued fraction. The first two are, for example, full measure conditions, and you can use the Gauss map, for example, to prove that they are full measure. And another interpretation is also dynamical, so that I want to mention for higher genus later. You can think of the modular surface, or better SL2R over SL2Z, which is the unit tangent bundle of it, as the space of linear flows on flat tori, the modular space of such flows. And on this space, you have Teichmuller, the geodesic flow, the hyperbolic geodesic flow. And Diophantine conditions dynamically can be interpreted as conditions when I follow a geodesic and I want to bound depth of or frequency of excursions into the cusp. So at some point, your geodesic goes to the cusp. So this is a point of view that you can keep in mind aside. Okay, and to go to higher genus, let me first go back to continued fraction entries. So how can you get continued fraction entries? You can think of them as a product of a renormalization procedure. So what is the idea? That I have a map of the interval and I look at the subinterval. And the renormalization means I look at the Poincare map on the subinterval. So I take a smaller interval, I wait until a point comes back under the map T to the smaller interval, and this gives an induced map, like a Poincare first return map. And then you can rescale it to make it again length 1. And I will say that the transformation of 0, 1 is infinitely renormalizable if I can choose, there is an algorithm that tells me how to produce a sequence of shrinking intervals, so smaller and smaller intervals, such that when I induce on these smaller intervals and rescale, I get a map of the same type or a map in the same family. For example, Let's take circle diffuse or even a rigid rotation to start with. These are renormalizable through the continuous fraction algorithm. So I'm doing here slow or additive continuous fraction. So you can take a map which looks like has 2 intervals, and you can choose a sequence of smaller and smaller intervals so that the Poincare map is always a circle diffuse, which looks like it has 2 continuity intervals on 0, 1. And the way to do it, you can each time cut the last interval, the shortest last interval. It doesn't matter how you do it, you can do it. So this type of algorithm you can also do for interval exchange maps and generalized interval exchange maps under suitable assumptions through an algorithm which was described by Rosy in the 70s and then studied a lot by Veitch in his work in the 80s. And we call it today Rosy-Veitch induction. And again, I don't want to define it, but there is a procedure to choose smaller and smaller intervals so that when you induce, you again have an IT or a generalized IT of the exact same number of intervals. And once you do this process, you can produce also some matrices out of it, matrices which are D by D, where D is the number of intervals. So for circle diffuse, 2 by 2. And these matrices have integer positive entries, non-negative entries. And you can think of them as incidence matrices. So let me tell you, if I choose, I want to know A and M, the matrix, I fix N and M. N and M are 2 times of my induction procedure, induction N, induction M. And I want to know the entry ij. So I or j is the index of 1 subinterval at time m. And I, which should be blue, is the index of an interval at time n. And this entry ij, I take my interval j, and I apply the map Tn. It moves around until it comes back for the first time inside the smaller interval. So this, I have these images, and I can count how many of these images of the green interval are in the light blue interval I. So this is the entry ij. Okay, it's not important, but I get these matrices out of the algorithm. And sometimes it's also convenient to accelerate the algorithm, so to do many steps at the same time. And there are various ways to accelerate. We want to maybe compact the algorithm so that you have a strictly positive matrix at every step, or that you have a matrix which gives the fixed contraction of the projective space. And these matrices, you should think of them as a higher dimensional, higher genus version of continuous fraction entries. And this is in particular, if you do this, compute these matrices for the continuous fraction multiplicative algorithm, acceleration, you get matrices of this form, 1 AN 0 1 or 1 0 AN 1. So in this case, the growth of the matrices is the same than the growth of the entries. And for Rosy-Veitch induction, you get D by D matrices. So you can think of these Diophantine-like conditions in higher genus as imposing control on the growth of these matrices for a suitable acceleration of the algorithm. But in dimension greater than 2, when D is greater than 2, it becomes also important to control hyperbolicity features. So you have a product of matrices. So for a fixed matrix, repeated, you may consider eigenvalues. For a product, you have a cocycle, and you may consider Lyapunov exponents when they are defined. So again, there is also an interpretation in terms of moduli space of higher genus linear flows. And in this case, you can look at fundamental domain in Teichmuller space for mapping class group action. And these matrices have to do with changes of base in homology of the surface when you change copy of the fundamental domain. And they are related to the Kontsevich-Zoric cocycle. So this is the point of view that generalizes the geodesic flow point of view in genus 1. And then you want to control these matrices, control for the positive acceleration, control excursion into the non-compact part. And why do I say that? Because we know a lot about Teichmuller dynamics, and we know a lot about hyperbolicity of the Teichmuller geodesic flow, and many results like seminal work on Zorich and Forni on Lyapunov exponents of this cycle, their positivity, and other more recent results like exponential mixing of the Teichmuller flow play a crucial role when you want to prove that some conditions have full measure. Okay, so now it's time to tell you some of these conditions and what results they allow you to prove. So let me go to mixing in area preserving flows, smooth area preserving flows. So here I just recall you that mixing is equidistribution of sets, or equivalently decay of correlation between two observables. So Arnold conjectured in the 90s at the time of Novikov work that if you have a flow in genus I with one saddle and one center, and you look at the minimal component, so you remove the part inside the saddle loop, this should be mixing, typically. And this conjecture was proven just a few years after by Sinai and Hanin for almost every rotation number under a Diophantine condition, like arithmetic condition, an grows less than some power of n. And the natural question then became what happens in higher genus. But higher genus took much longer to be understood because in higher genus, mixing or not mixing depends on the type of singularities. So now we have a full picture. So if the flow has only simple saddles, so only simple saddles, and it's typically uniquely ergodic and minimal, but I proved about 10 years ago that it's not mixing. On the other hand, you can nevertheless show that it's weakly mixing. I also proved that. And it's a full measure result, but in the complement, there are exceptionally also mixing examples, which were produced by John Chaika and Alex Wright. Conversely, the other case is when you have actually centers or maybe saddle loops. And in this case, you can have several minimal components, but each minimal component, typically, when you restrict the flow to each minimal component, you see mixing. And this started from my work, then was later proved in a special case, and Ravotti, my PhD student, later proved it in generality, and also gave some quantitative mixing estimates. So there is mixing, but mixing is slow. And slow means that the decay of correlations is super polynomial. So it's bounded by some power of log. So this is a slow chaos feature. So how do you prove these results? Well, you crucially need good Diophantine-like conditions on the Poincare recession, which is an interval exchange map. So for example, for this result on mixing, I introduced the mix, what I call the mixing Diophantine condition. So this is a condition on the cross of these matrices. Again, there's a suitable acceleration of the algorithm. Balanced acceleration, and you want these matrices to grow polynomially. It's very similar to Sinai-Hanin condition once you have the right acceleration. And to prove that it has full measure, you really need results by Avila, Guesel, and Yokos in their paper on exponential mixing of the Teichmuller flow. Contrary, when you want to prove absence of mixing, you also need a Diophantine condition in higher genus. This is more subtle, and it involves a series, backward series. So you want infinitely many times. So when you look back, your matrices grow not too fast, so that such a certain series converge. This condition didn't have a name. It's hidden a bit in the paper. But the idea is that these conditions, in the absence of mixing or mixing case, control equidistribution of orbits, of trajectories of your flow or orbits of the Poincare map, and they allow you to control shearing. So shearing is behind mixing. It's a key geometric phenomenon which is used to prove mixing. And this is just a schematic heuristic idea. What is shearing? So it's a phenomenon well known for horocycle flow or unipotent flows. So if you have 2 points and flow them, when you have shearing, they flow parallelly, but at different speed. So in my picture, the blue point is much faster than the red. And therefore, if I look at the transversal to the 2 points, an arc connecting them, when the blue flows faster, the arc, transverse arc shears. And shears, here we are in dimension 2, so the shearing is automatically in the flow direction. And this type of geometric mechanism and the quantitative version of the shearing was introduced, well, it's used a lot in homogeneous dynamics to study unipotent flows. And in particular, Marina Ratner, in her seminal work on the horocycle flows, introduced a quantitative form of shearing that we call nowadays Ratner property, and has striking consequences on rigidity of joinings, and it's also used in measure, different form in measure classification and so on. So a question which I understand was raised by Jean-Paul Duvenot, and also Marius Lemanchik has advertised it quite a bit, so I heard it from both of them, is whether you can prove this Ratner property for flows on surfaces. Problem is that you have singularities, saddles, and the saddles, if you control flow shearing, you may control it as well as you want, but when you hit a saddle, then your trajectories, will, okay, I don't have it. After hitting, being splitting by a separatrix, they take different histories, and you lose control of shearing. Singularities lose control of shearing. So what do we do then? Well, nevertheless, with Adam Kanigowski and Joanna Kuaga-Shimus, we could prove that when you have traps, typical smooth area preserving flows has not the original Ratner property but a variation of the Ratner property. And you can use this property to prove the typical smooth area preserving flows with saddle loops is not only mixing, but actually mixing of all orders. So that means that not only the correlation between 2 observables goes to 0, but also goes to the mean, also the correlation between n observables can be controlled. And what is the variant, or the variation of the Ratner property? It's a variation introduced by Fayyad and Kanigowski to study flows in Genus I, and it's called switchable Ratner property. I don't want to enter into it now. But again, to prove the Ratner property, this variant of the Ratner property in higher genus, we need a Diophantine condition expressed in terms of cross of these matrices. And this is a series where you actually look at only matrices which are exceptionally high and build a certain series. And it's very reminiscent, or very similar formally to the condition that Fayyad and Kanigowski used in Genus I to study Arnold flows. And it again uses, the proof of full measure exploits some properties of a suitable acceleration. But here, maybe more than the condition, it's actually, you have to deal with singularities. So this condition allows you to throw away sets where you don't have good shearing estimates at all scales. And then for the sets where you don't throw away, where you don't control shearing, you have to be careful about singularities and play with the full strength of the switchable condition. Okay, this is quite technical, but now I want to do one different instance of Diophantine conditions in higher genus related to linearization questions. So when we have, for the local linearization problem, so this means I start from standard IT, and I look at generalized ITs, which are like in my picture, a small perturbation of linear IT. And maybe you start by perturbing away from the discontinuities. It's called simple perturbation. And then you ask if this perturbed generalized IT is, if you start CR close, if you're a CR small perturbation, are you conjugating? And with what regularity? And sorry, if you start, so if you look, sorry, no, if you look, CR plus 2 close, okay. If you look at the generalized IETs, let's say smooth generalized IET, piecewise smooth, which are CR conjugated to a standard IET, it turns out that differently than in the case of circle diffuse, they will be rare and they will form a finite codimension submanifold. So in a small neighborhood, only a submanifold of a certain finite codimension will give the CR conjugacy class. So this is a result proven by Marvin Musa and Yokos for almost every standard IET under a condition that they call rod type for R and is 2. And and Selim Ghazouani has recently proven a result for the C1 conjugacy class, but for a measure 0 for now set of IETs. And again, the condition used by Marvin Musa Yokos is the Diophantine-like condition about what they call it rod type in analogy to the rod type condition. It controls in a similar way the growth of this matrix continued fraction entries. And not only that, not only the growth, but this is an example where they also need some hyperbolicity assumptions. They need to use Ozellet's genericity and control positivity of exponents in the restricted rod type condition. So with Selim Ghazouani, we looked at related another question about called the rigidity, which was indeed suggested as a conjecture by Marvin Musa and Yokos, which is the following type of question. So if I know that I have a topological conjugacy between a generalized IET and the standard IET, can I say something about the regularity? Can I say that the conjugacy is actually C1? So you need to assume also that the generalized IET has boundary 0. This is a necessary condition for C1 conjugacy. It's a local condition at singularities, but Marvin Musa Yokos conjecture that this is the case. And with Selim, we proved this for Genus II, for Poincare recessions of Genus II flows. And again, it's a nice interpretation in terms of foliations on surfaces of Genus II with Morse type saddles. And then if you have such a foliation and which is linearizable in C0, so conjugated topologically to the linear model, the conjugacy is C1. And how do we prove this? We use renormalization and study how it acts as an operator on generalized IETs globally. It's a global result, not a local result. And we prove a dynamical dichotomy. We prove that either renormalization is recurrent in C1 sense, and in this case, we can prove C1 conjugacy in some sense, following the blueprint of Hermann work in circle diffuse. Or renormalization, this is the typical case, renormalization diverges, in which case we say something about the way in which it diverges, and it's driven by what we call an affine shadow. And then when we have a C0 conjugacy, at least for now in Genus II, we can exclude the second case and reduce to the C1 conjugacy. So, and again, when we want to prove this dynamical dichotomy, we prove it for almost every almost every rotation number, and we need a Diophantine condition of full measure, which we call regular Diophantine condition, and this is a quite subtle condition because you have to accelerate your induction, Rosevich induction, to start from a Ozellet's generic IET, and then have a special acceleration where you have effective Ozellet's estimates or quantitative Ozellet's control. And then you'll get in the condition you want convergence of some infinite series. Infinitely many times you want to look forward or backward and have some series which involve how the matrix acts on the stable or unstable space, the projection to the stable unstable space, and the norm. So it's a quite refined Diophantine condition that we need in this result. And it's kind of curious that also in some recent work with Franczek, we looked at a very classical phenomenon by now about deviations of ergodic averages. So maybe I will skip this slide. So you can study ergodic integrals, or maybe 5 minutes is good. So you can study ergodic integrals of smooth observables over an area preserving flow. And it's a phenomenon called Kontsevich-Zoric phenomenon, that these integrals grow at time t, grow like a power of t, or oscillate, but the size of the oscillation is power of t. And the powers that appear can only be finitely many, so G, where G is the number of the genus. This is called power spectrum of deviations. And it was conjectured, or in a special case proved by Zoric, then proved by Forni, and Avila and Viana proved that the exponents are all different, and Buffetov refined the result by giving an asymptotic expansion. So you can really write an ergodic integral as combination of G cocycles, or G functions ui, each of which grow like one of these powers, oscillate like one of these powers, plus an error which is smaller than any power, or sometimes you can say it's bounded. And with Franczek, we recently gave a new proof of this result for smooth function. And the original result assumes that the function is 0 at the singularities. And we removed this assumption in the case of simple saddles. And Kim and Franczek also proved this, extend the result to functions which are non-zero at the degenerate saddle. And then they get some additional power terms, additional power exponents. And the new proof extends Marmi Musayoko's work for the cohomological equation and requires a Diophantine condition in higher genus, which is very similar to the one that we use for Selim for linearization. So it has series which depend on the past and the future and are controlled by effective oscillators, or effective hyperbolicity. So these conditions really seem to be recurrent. And I didn't say in the case of Selim, the blueprint is somehow reminiscent of proving existence of a stable manifold for a hyperbolic operator. The nature of these conditions is reminiscent of this process. That's what we need to build the shape, the shadow. Okay, last slide. I'm almost finished. I want to mention some future directions and questions. So what is happening now, what we don't understand yet well, is the spectral theory. So what is the spectrum of these locally Hamiltonian flows seen as a Koopman operator on L2 observables? And there are some results in Genus 1 and 2. So Fayyad, Forni, and Kanigowski have studied flows in Genus 1 with a stopping point and proved that typically they have countable level spectrum. In Genus 2, with Chaika, Franczek, and Kanigowski, we have a result about typical flow with two simple isomorphic saddles. And here the spectrum is singular. So the general case, so the case of higher genus, will certainly require new Diophantine conditions. And another question is also disjointness of rescalings between these flows. So you can see Marius Lemanchik ICM talk on Möbius orthogonality as a motivation for disjointness. And here we have some work with in Genus 1 with 4R node flows with Lemanchik and Kanigowski about disjointness. And again, higher genus version of these results, some of which we are thinking about or working on, will require new Diophantine type conditions. And what is interesting is that you need to have Liouvillean type conditions. So you need typical, but you need some sequence where the matrices grow. So you have some generation, you go to infinity in moduli space, and then you want to control the way that the generation happens. So in higher genus, you can degenerate in various ways, and you may want to control the geometry. And last questions. The weakness of this type of conditions in higher genus is that when they require Ozelledets type of conditions or positivity of exponents, they are not explicit. So it's apart from periodic type, so when you have a same matrix and then you can compute eigenvalues, or they are hard to check. So a challenge would be maybe in some special locus or on some setting, you can actually check these conditions. Question, not clear. And the last one, maybe you want to understand exceptional behavior. So outside of this full measure set that we understand of rotation of conditions, can something different happen like Chaika right for mixing? And it's also not so clear what are inclusions. Some of these conditions imply each other, others maybe to be understood, maybe not so difficult. And optimal conditions are probably out of reach. So we can understand exceptional behavior. We have a full measure set. What is the optimal condition? In genus 1, we have optimal results like Hermann-Joch's theorem. In higher genus, it's probably very difficult to dream for optimality, but I leave it as an open question. And I stop here. And again, I'm very happy to welcome questions on the Discord chat, since there is no time now or no opportunity now, but I'm happy to have a discussion with anyone who wants to ask something. Thank you.
Thank you very much for the beautiful lecture. And as it was already said, you can ask questions through Discord. I think this is the end of this session. Thanks again for your lecture. And I hope next time we will see each other in person.
Yeah, it'd be nice. Yeah.
Okay, maybe the...
Yeah, it's offline, right?
One moment, please.